So here what we're going to do in this series is talk about what we call resistor series. We're going to have a battery and a bunch of resistors hooked up in a certain way, combination of parallel and series combinations. And we're going to learn how to find what we call the equivalent resistance, how to find the current in the circuit, and how we find the current in each branch of the circuit, as well as the voltage drop across each resistor. And a lot of that has to do with knowing how to take a resistor circuit and simplifying it down to a single equivalent resistor for the entire circuit. And so we're also going to have some videos that will show you how to actually do that with some more complicated circuits as well. So let's start with this one, which is a fairly straightforward one. So what we have here is we have two parallel branches, and they're hooked up in series. And series means that one is hooked up after the other, and any current flowing through the circuit has to go through both branches. That's how we know the branches are in series. And since current could split up into two directions here, that's how we know that these are in parallel. So what we're going to do is to figure out how much current is flowing through the circuit. So that's one of the questions, I equals question mark. And then we're going to figure out I in each branch, and also how much voltage drop there is across all the resistors. So the V sub R is equal to question mark. So the sub R means the voltage across the resistor. All right, in order to accomplish that, we're going to have to simplify the circuit. So we have to find what we call equivalent resistors. And usually how that's done is by slowly going from the most complicated situation to a more simple situation by combining resistors and replacing them by a single equivalent resistor. So the first thing we're going to do, and let me get a different color, we're going to take these two resistors right here, combine them into a single resistor. We're going to take those two resistors, combine them into a single resistor. And since they are in parallel, the way to do that, you could say that 1 over R total, or the equivalent resistance, so we use either total or equivalent kind of synonymously. So 1 over R total is equal to 1 over R1 plus 1 over R2. If there's only two resistors, there's actually an easier equation we can use. We can say that R total is equal to the product over the sum, which is R1 times R2 divided by R1 plus R2. So using this technique, we have the two resistors, so we have 6 times 2. Notice how I don't write the ohm sign because it makes it cleaner and easier to work with, divided by 6 plus 2, which is equal to 12 divided by 8, which is equal to, looks like 3 halves, right? That goes, yep, so 3 halves. So our equivalent resistance of these two resistors together is 3 halves. So we could take these two resistors away, replace it by a single resistor that is 3 halves of ohm, and you get electrically exactly the same response. So our new circuit will look like this, with the first resistor replaced by a 3 over 2 ohm resistor. There we go. Now the second one, we do the same thing. We use those two resistors. So we have R total is equal to R3 times R4 divided by R3 plus R4. So again, is the product over the sum. That would be 12 times 6 divided by 12 plus 6. That would be 72 divided by 18. And that goes, 18 goes 72 exactly 4 times. All right, so we replace the second resistor by a 4 ohm resistor. We still have our battery. The battery had a potential difference across it of 55 volts. All right, so now we went from this circuit to this circuit. This resistor is the same as these two in parallel. This resistor is the same as those two in parallel. But we're not done yet. Now we have two resistors in series. And of course, when you add resistors in series, you simply add them up. So here you could say R total equals R, well, let's call this R5 and R6. Those are the equivalent resistors. So that would be R5 plus R6 because these are series resistors. They're in series, one after the other. Again, any current going through the circuit has to go through both resistors. There's no choice. That means they're in series. And so in this case, we simply say 1.5 ohms, because 3 halves is 1.5, plus 4 ohms. And so that would be a total of 5.5 ohms. All right, so we can now replace this circuit with an even simpler equivalent circuit. Like so, we have now a single battery with a single equivalent resistance. So R equivalent, EQ for equivalent, is now equal to 5.5 ohms. And the battery is equal to 55 volts of potential difference across the battery. All right, so now electrically, if you had, for example, a black box with 2 leads sticking out, and you went in and probed around trying to figure out what the current, the voltage, and the resistance is, you would get this result, and you couldn't tell if you're talking about or working with a circuit that looks like this or with a circuit that looked like that. Electrically, they're identical. So now we can use Ohm's law. Ohm's law says that the current in any circuit is equal to the voltage across the circuit divided by the resistance. So in this case, that would be the total or equivalent resistance. This is 55 volts divided by 5.5 ohms, which is equal to 10 amps. Which now means that the current in the circuit is 10 amps, which means that the current flowing through the circuit this way, I equals 10 amps. That's the total current. Now the next step, we want to go ahead and try to figure out how much current flows through each branch. So we can see that there's going to be current going in the upper branch and current going down the lower branch. Kind of like a river. When a river gets to a place where there's an island in the middle of the river, some of the water goes to the left, some of the water goes to the right, and more water goes to the side where there's less resistance, less water goes to the side where there's more resistance. So where you have more resistance, less current will go. Where you have less resistance, more current will go. Since there is 3 times as much resistance as you see over here, there only will be 1/3 of the current going to the top branch and compared to the current going to the low branch. But how do you actually figure that out? How do you actually calculate how much current goes through each branch? Well, if you call this the total current, I total is 10 amps, then for the top, I going to the top, that's going to be equal to I total, the amount of current coming in, times the following ratio. In the numerator, you write the resistance of the other branch. So we're trying to figure out the current in the top branch. You write the resistance of the lower branch divided by the sum of the two resistors, 2 plus 6. That will give you the current in the top side of that circuit. So this will be equal to 10 amps times 2/8, which is 1/4, which is equal to 2.5 amps. So this means that 2.5 amps goes to the top branch, which of course, if there's a total of 10 and 2.5 goes this way, you'd expect 7.5 to go this way. Again, we can figure out using the equation, I at the bottom is equal to I total times, now you take the resistance of the other branch, so now we want to know the current through here, and so what we're going to do is take the resistor of the other branch divided by the total. And so this is equal to 10 amps times 6 divided by 8, which is equal to 7.5 amps. So you can see how nice that works. That equation works really nice when you have a branch with just 2 resistors like that. We can do the same for the second branch. Notice that the 2 currents then come back together. Over here you'll have 10 amps again. Notice the top branch, I at the top will be 2.5 amps, and I at the bottom will be 7.5 amps. They come together, forms 10 amps again, and now the current will split up again over here. And again, how do you figure out what the current will be? Well, you go I at the top is equal to the 10 amps coming into the branch. And now, since we're trying to figure out the I at the top, we take the resistance of the other side, which is 6, divided by the sum of the 2, which is 6 plus 12. So that would be equal to 10 amps times, that would be 6/18, which is 1/3, which is equal to 3.33 amps. Okay, 6 divided by 18 is 1/3. And then we do it for the bottom. I at the bottom is equal to 10 amps times the resistance in the other branch. So now we're trying to find the current in the lower branch. So we take the resistance of the upper branch, 12, divided by the sum of the 2, 6 plus 12. And so 12 divided by 18 is 2/3. So that would be 10 amps times 2/3, which would be equal to 6.67 amps rounded off. You can see that the 2 together add up to 10 amps. Then they come back together, and then it's 10 amps again. All right. Now, how do we figure out the voltage drop across each of these resistors? So if we want to know the voltage drop across R1, I'm running out of room here, but let me just put it right at the bottom. So the voltage across R1 is equal to question mark. So how do we do that? Well, let's go back to Ohm's law. Ohm's law tells us that I equals V over R. So if we take this equation and solve for V, we can then say that V equals I times R. So all we have to do is take the current in that branch and multiply it times the resistance. So V through R1 is equal to the current through R1. And the current through R1 was 2.5 amps. And the resistance, 6 ohms. So that would be 6 times 2.5, which is 15 volts. So that tells us the voltage drop across the top resistor there, R1, is 15 volts. Now, we know that across any parallel branch, the voltages have to be the same, so we expect the voltage here to be 15 volts as well. But again, we can figure that out. So we have voltage across R2 is equal to, we take the current through R2, which was 7.5 amps, 7.5 amps, and the resistance of R2, which is 2 ohms. You can see that will be 15 volts as well, just like we expected. All right, we can do that again for the second branch, or we can be kind of smart about it. Think about that the total voltage drop across the circuit has to be 55 volts. The battery provides a voltage increase of 55 volts, and then the volts will drop across the two branches. So if we have a voltage drop across here of 15 volts from this point to this point, and sometimes I just kind of denote it like that, that says that the voltage drop between these 2 points is 15 volts, then what drops across here? Well, that must be the remainder. 55 minus 15, my guess would be that this would be a 40 volt drop. And just to make sure that we did it correctly, let's find out the drop across this one right here. Notice that I at the top, right here was 3.33 amps. So I at the top for this branch was equal to 3.33 amps. And so therefore we can say that the voltage across R3 is equal to I times R, right? Voltage is I times R. So we take the current, 3.33 amps, and we multiply it times the resistance of that branch, which is 12 ohms. And so what is that altogether? That would be 33 times 6.8, and indeed, that is exactly 40 volts. So you can see, you can do it that way as well. So here's a nice, very nice example. We have parallel and series combination resistors. We find first the equivalent resistance, first the equivalent resistance of each branch, then the total equivalent resistance for the circuit. That allows us to find the current in the circuit using Ohm's law. I equals total voltage divided by total resistance, 10 amps. We now take the 10 amps and try to figure out how much current goes through each branch. We have that very nice nifty equation. For the current at the top is the total current, at 10 amps coming in, times the ratio of the resistance of the other branch divided by the total resistance, the two sum together. We do that for each branch, and we find the current in each case for all 4 branches like that. And then finally, to find the voltage across each resistor, we know from Ohm's law that V is I times R, the current through the resistor times the resistance. So here in our example, we take the current through the resistor times the resistance, gives us the voltage drop. And remember that whatever the battery gives you in voltage, this is a step up in voltage. When you go around the circuit, you go back down to the beginning where you started. And sometimes we put like a little reference clause in there saying, if we call this 0 volts, then this would be at 55 volts. We come around here, we drop, as we noticed, 15 volts. So we go from 55 down to 40 volts. And then from this point out to go to there, you go back to 0 volts, back to ground, and back across the battery and so forth. And that's how you do that problem.